Ever been stuck on one of those coding problems with a grid of data? The ones where you have to find a path or count different regions or maybe even simulate how something spreads? Well, what if I told you there's one powerful technique that can handle almost all of them? Today, we are going to unlock that master pattern for grid traversal, which you'll often hear called the island pattern. Let's dive right in.
So to really get this whole concept, you just need one super simple mental model. Think back to the paint bucket tool in, any old school graphics program. You click on one pixel and whoosh, the color just floods out and fills up all the connected pixels that are the same color. And that's it. That's the core idea, the intuition behind what we're going to be doing. It's often called a flood fill algorithm for that exact reason.
And look, this simple idea isn't just for one niche problem. It's like a master key that unlocks solutions to a whole bunch of complex challenges. We're talking about everything from counting groups of land on a map to figuring out how long it takes for something like, say, rotting oranges to spread across a crate. It's surprisingly versatile.
All right, so let's put a formal name on this. What is the island pattern? Well, at its heart, it's really just a collection of techniques that all use that flood fill idea to give us a structured, systematic way to explore connected cells inside any grid or matrix.
So you might be wondering, why is this pattern so good? Well, first off, it naturally finds and explores entire connected groups for you. That means you get to skip all those messy and efficient brute force checks, and you're not double counting cells. It's really efficient because you only touch each cell once. And for certain problems, one of the methods we'll use, called BFS, is perfect because it models how things spread out in parallel, kind of like ripples spreading in a pond. Okay, to really master this pattern, you just need a few basic building blocks. Let's think of this next part as putting together your core toolkit. Once you have these pieces, you'll be ready to tackle pretty much any grid problem they throw at you. And honestly, there are only 3 essential things you need to nail down. First, you've got to define your neighbor directions. Are we only looking up, down, left, and right, or are we including diagonals too? Second, and this one is absolutely crucial, you need a way to keep track of where you've already been. This is what prevents you from getting stuck in an infinite loop. And third, you just have to pick your traversal method. Are you going to go with depth first search or breadth first search? So let's talk about that choice, DFS versus BSS. It's all about picking the right tool for the job. Think of DFS, or depth first search, like you're exploring a maze. It goes deep down one single path as far as it can before it backtracks. This makes it awesome for just counting up the size of an area or simple traversals. BFS, on the other hand, is breadth first search. This is more like those ripples in a pond. It explores everything one level at a time, spreading outwards. And because of that, it is absolutely perfect for finding the shortest path or anything that spreads over time. The good news? They're both really efficient. They both run in what's called O&M time, which just means their speed scales really well with the size of the grid.
All right, we've got our toolkit. Now for the fun part, let's see this thing in action. We're going to go through a sort of cookbook of classic grid problems, and you'll see just how many different recipes use these same core ingredients. First up, the absolute classic, number of islands. The goal here is just to count how many separate groups of ones there are, and the logic is just beautiful. You just scan through the grid cell by cell. The moment you find a piece of land, a 1, that you haven't seen before, you know you've found a new island. So you add 1 to your count, and then right away, you launch your flood fill to visit and mark that entire island, so you don't accidentally count any part of it again.
Okay, now let's build on that. What if, instead of counting the islands, you want to find the area of the biggest one? Well, it's just a tiny little tweak to our last solution. This time, when our flood fill function explores an island, we just have it return the number of cells it found. Then all we do is keep track of the biggest number we've seen so far. See how we just modified the pattern slightly? It's that easy. Now for a really clever twist. What if you need to find all the regions that are completely surrounded by X's? You might think you need to search from the inside, but the trick is to flip the logic completely. Instead, start your flood fill from all the O's on the border of the grid. Anything they can touch is considered safe because it can reach the edge. Then you just go through the grid one last time, and any O that you didn't mark as safe, well, it must be surrounded. This next one, number of enclaves, uses that same brilliant peel from the edges technique. The goal is to count the land cells that can't reach the boundary. So, just like before, you start by finding all the land cells that can reach the boundary. You run your flood fill from every land cell on the border and turn them all into water. And then, you just count the land cells that are left.
Okay, what about a closed island? A closed island is just one that doesn't touch any of the borders. So how do we find them? Well, you can probably guess by now. First, we use our border trick. We run a flood fill from every land cell on the border to get rid of any island that's connected to an edge. Then, on whatever's left over, we just run our original number of islands code. It's a two-step process using patterns we already know.
Here's a great one: rotting oranges. This problem is a perfect showcase for breadth-first search. See, you start by putting all the oranges that are already rotten into your queue. Then, each step, or level, of your BFS represents 1 minute passing. In that minute, all the rotten oranges infect their fresh neighbors. You just keep track of how many minutes or levels it takes until there are no fresh oranges left.
And that leads us right into finding the shortest path in a matrix. Remember how BFS explores level by level, like ripples? Well, that property makes it the perfect tool for finding the shortest path in any grid, where every step costs the same, because it explores all paths of length 1, then all paths of length q, and so on. The very first time it reaches the end, you know for a fact that you found the shortest possible route.
All right, this next one, Pacific-Atlantic water flow, seems really tricky at first, but the solution is so clever. Instead of trying to trace water flowing downhill from every single cell, which would be a mess, you just reverse the problem. You start at the oceans and work your way uphill. First, you do a flood fill from the Pacific to find all the cells that can drain into it. Then, you do another one from the Atlantic. The answer is just the list of cells that showed up in both of your results. Super elegant, right?
Okay, we've talked through a ton of high-level logic. Let's bring this down to earth and make it a little more concrete. We're going to take a quick peek at how these ideas actually translate into real Go code.
Hey, remember our toolkit? The first thing we needed was to define our neighbor directions. Well, here's how you do it. You just create a simple array of arrays. Each little inner array is just a coordinate pair that represents one move. Down one, up one, right one, and left one. When you loop over this, visiting neighbors becomes super clean and simple.
And here it is, the heart of the number of islands solution. It's just a standard nested loop that scans every single cell in the grid. But that if condition inside, that's the magic. It's asking, is this cell a piece of land, and have we not been here before? If the answer to both is yes, it knows it's just found a brand new island. So it adds 1 to the count and kicks off the flood fill.
And this right here is the flood fill engine itself, the DFS helper function. That big if statement at the top is just a bunch of safety checks. It's asking, are we off the grid? Have we already been to this cell? Is this cell just water? If any of those are true, we just stop. Otherwise, we mark the current spot as visited, and then we make that recursive call for each one of its neighbors to keep the search going.
Okay, before we wrap things up, let's quickly go over a final checklist. These are the key tips and common mistakes you want to keep in mind so you can apply this pattern perfectly every single time. So, here are the big takeaways. First, always confirm your connectivity. Does the problem want 4 directions or 8? For anything involving enclosed or surrounded regions, your first thought should be to start from the borders. Remember, BFS is your go-to for shortest paths and anything that spreads. DFS is great for simple counting, just watch out for really deep grids. And finally, I can't say this enough. Your system for marking visited cells has to be perfect. That's where most of the bugs happen. And that's really it. That's the island traversal pattern. It's not just one algorithm. It's a powerful mental model and a whole toolkit. You've now got the entire cookbook. So the only question I have for you is, which grid problem are you going to solve first?